You will inflate your lungs roughly 20,000 times today. It happens so automatically, we rarely think about the massive mechanical effort required to pull it off. If we zoom in to this cross-section of the lung's architecture, we find the terminal endpoints of our airway, the alveoli. An adult human has about 200 million of these microscopic sac-like structures branching off the alveolar ducts. If you took the incredibly thin walls separating these air spaces and laid them flat, they would cover an internal surface area of 75 square meters. But this massive surface area creates a physical paradox. The inside of each alveolus is wet. Because these structures surround a central airspace, that liquid forms an air-water interface, and that interface generates surface tension. The physics here are dictated by the Young-Laplace equation. As you can see in this diagram, the surface tension of the liquid creates an inward collapsing force. To keep the alveolus open, that tension has to be perfectly balanced by the outward expanding force of the gas inside. Without an intervention, the surface tension of water would physically crush these air sacs every time you exhale, a condition known as atelectasis. On top of that structural threat, this fragile membrane is entirely exposed to the outside world. With every breath, an influx of airborne pathogens, dust, and particulate matter is pulled deep into these microscopic pockets. Without the specific biological safeguards we've evolved, the physical architecture of the human lung would be unable to maintain the gas exchange surface needed to sustain life. The reason we survive our first breath is thanks to a specialized group of cells embedded right in the alveolar wall. These are type 2 pneumocytes, and their job is to continuously secrete a highly complex mixture of proteins and lipids called pulmonary surfactant. The primary lipid component here is a molecule called DPPC. As shown in this cross-section, these surfactant molecules adsorb directly to the air-water interface. Their hydrophilic heads submerge in the water layer, while their hydrophobic tails point straight up into the open airspace. By pushing apart at the surface, they dramatically reduce the tension of the liquid layer. This chemical action creates what clinicians call pulmonary compliance. It makes the lungs pliable, drastically minimizing the mechanical pressure and the physical work you have to exert to draw your next breath. We can see exactly what happens without this equilibrium by looking at premature infants. Babies born before 20 weeks gestation haven't yet developed the specific cellular structures, called lamellar bodies, required to produce surfactant. When these infants try to breathe, they develop infant respiratory distress syndrome. Because they lack surfactant, the raw physical force required to pry open the collapsed, highly tensioned airways literally tears the lung's delicate epithelial tissues apart. Fortunately, modern medicine has found a reliable workaround. Doctors now coat the lungs of these premature babies with artificial surfactants, medicines so critical they are listed on the WHO's model list of essential medicines, which immediately lower the surface tension and save their lives. The mechanical act of breathing relies entirely on this continuous chemical secretion to stabilize the air-water interface and prevent total alveolar collapse. Physical collapse is only half the battle. To handle the biological threats, the lung relies on a roaming immune enforcer, the alveolar macrophage, commonly known as the dust cell. Their primary function is phagocytosis. In this highly magnified view, you can see one of these massive asymmetrical cells rapidly extending its pseudopods to engulf foreign particulate matter. Millions of these macrophages patrol the alveoli every day, swallowing up toxic pollutants, consuming harmful bacteria, and clearing dead tissue. Once these cells are completely gorged on debris, they migrate out of the alveoli. They move into the bronchioles and ride up the mucociliary escalator, a sweeping layer of mucus and hair-like cilia to be swallowed or expelled through the pharynx. While surfactant keeps the physical structure from crushing inward, this living defense grid guarantees the delicate respiratory membrane remains sterile and functional. When severe infections or conditions like congestive heart failure overwhelm these cellular defenses, the entire ecosystem breaks down. This leads to pulmonary consolidation. The normal, compressible air spaces of the alveoli become completely filled with liquid, whether that's inflammatory fluid, pus, or blood. The tissue swells, hardens, and instantly loses its ability to exchange gas. Even the macrophages fail in this environment. In congestive heart failure, blood backs up and red blood cells leak into the alveoli. The macrophages gorge themselves on these red blood cells, filling with iron pigment and transforming into heavy, useless bodies known as heart failure cells. Looking at this side-by-side comparison, the clinical manifestation is obvious. On the left, a healthy X-ray shows normal, black, aerated lungs. On the right, consolidation has replaced the air with fluid, turning the affected lung lobes into a dense, opaque white mass. Clinical suffocation results from the total microscopic destruction of the alveolar air-water interface, rendering the membrane useless for gas exchange. To measure the integrity of this membrane in real time, doctors rely on the DLCO test, short for the diffusing capacity of the lungs for carbon monoxide. During the test, a patient inhales a specific, safe mixture of trace gases, containing 0.3% carbon monoxide. This gas is chosen because it binds to the hemoglobin in our red blood cells 200 to 300 times more avidly than oxygen does. By capturing and analyzing the breath the patient exhales 10 seconds later, clinicians can calculate the exact rate at which those test molecules successfully diffused across the surviving alveolar membrane. As you can see in this diagnostic flowchart, specific reductions in the DLCO score, marked here as a decreased D, can be compared against the total alveolar volume. This allows doctors to pinpoint the exact nature of the pathology. A low DLCO combined with a high lung volume indicates emphysema, which destroys the gas-exchanging surface area. A low DLCO with a shrinking lung volume points toward fibrotic disorders that physically thicken and scar the membrane. Every breath requires a complex, synchronized effort between lipid chemistry and mobile immune defenses to prevent the lungs from collapsing or succumbing to environmental debris.